In today's video, I'm going to be talking about the Arctic tundra and specifically the water cycle in the Arctic tundra. This is for the OCR A-Level Geography spec, and I've highlighted in the Earth Life Support Systems part of the spec where we speak about the water cycle, physical factors that affect it, and the seasonal changes in the water cycle. So here's a map of the Arctic tundra. It's a major biome that covers 8 million kilometers squared and can be found in northern Canada, Alaska and Siberia. In terms of physical factors, the obvious thing to notice is that it's an area where the temperatures are incredibly low. This is largely due to the fact that it has a negative heat balance for 8 to 9 months a year, so more heat is actually lost to the atmosphere than is actually gained to the surface from solar radiation. Because of that, the temperatures are extremely low, so minus 15 degrees C is an average temperature, but it can get as low as minus 40 in the deepest winter. This lack of temperature and radiation obviously is a massive driver in how the water cycle acts, and it has an incredibly severe climate. So most of the year, 8 to 9 months a year, it will be below freezing, so below 0 degrees C. And there will also be very, very little amounts of precipitation, so somewhere in the region of 50 to 350 millimetres a year on average. That's about 10% of what you would get in the Amazon per year. So extremely low temperatures, very, very little precipitation of any form. Another physical factor that has an impact on the water cycle and carbon cycle is permafrost. And as you can see, this wedge of ice, essentially what it is a layer that is permanently frozen throughout the year of soil and ice that is just below the surface, and that will stay as a kind of rigid barrier for most of the year. There are changes to the layer above it, but that will stay completely frozen throughout the year. We can see here some examples of slight variations in the vegetation. In the summer, we get those temperatures just creeping above freezing, where most of the year they're not, and we get some more exposure to longer hours of daylight. So we get a short growing season for the plants. That's when all of the kind of greening of the Arctic would happen. But the plants have adapted to this short growing season, so they're very, very low to the ground. They have very small leaves. So we can see that they are not giving off a lot of water via transpiration, but they also won't require a lot of precipitation to be able to grow because they know they're not going to be able to get it in this environment. If we go really far north into the high Arctic, conditions are much more severe. There's even less vegetation and lots more bare ground. So we can see there are spatial differences in the vegetation in this area. And also when we see the temperatures changing between summer and winter, even if it's a marginal change, that shows that there is changes over time, which will obviously affect the water cycle. We just talked about changes over time within a year. It's also interesting to talk about the fact that climate change, due to the enhanced greenhouse effect, is leading to long-term potential change to this environment. And because we're getting higher temperatures, we have the potential that there will be areas of the Arctic that will become more green. As temperatures go up, there is better temperatures for them to be actually grow vegetation. And we see this dark area in northern Quebec, which has seen an increase in greening since temperatures have started to rise. We don't know the full extent of that and how that will affect the water and carbon cycle, but it is something that is interesting and will change those cycles in some shape or form. So I'm now going to talk about the water cycle and the specific conditions. Largely, most of this is related to the low temperatures, but we've got very limited precipitation, most of which will only fall as snow, less than 100 millimetres in most areas. But because of those low temperatures, we're going to not have much of the moisture stored in the atmosphere because there'll be low absolute humidity. So the air just simply can't hold much water, where in the Amazon, because it's so warm, it can hold incredible amounts of water in the atmosphere. So very little of this moisture is going to be stored in the atmosphere. We also talked about plants being very limited in their kind of ability to grow, so there'll be limited transpiration, therefore, from the surface. This, again, we said this could change as climate change increases, but we can see that the flows of water are therefore pretty slow, limited precipitation, limited transpiration going back. And we're seeing that in this picture here, a lot of it would be stored on the surface. And this is largely because of permafrost. So this permafrost that we said was that permanent layer of frozen soil. That is a barrier to any infiltration of water or put deeper percolation. And so we get very limited aquifer storage. Soil moisture is very limited. And so when we do get water appearing, which we'll talk about in the summer, it's not going to be stored anywhere really below the surface. This essentially acts as a brick wall for stopping any water going deeper than the surface. The only area that does change, this is a seasonal change, so we get a thawing of the top layer of the soil, what we call the active layer, which is that really small top layer in the spring and early summer, and therefore that would have a higher water content in the soil, but that would be very limited to that top layer. We talk about seasonal change earlier on. We can see that in the winter it's below zero, and in the summer it gets above zero. That affects the water cycle in an obvious way. So in the winter, most of the kind of water will be stored as permafrost or snow on the surface. Obviously, as those temperatures creep up in the summer, what happens is we'll start to see that liquid water on the surface. So that's that active layer that's melted, and because the permafrost stops it from going down, it kind of sits on the surface. And there are other physical factors I'll talk about later on that kind of aid that. So there is a little bit of evapotranspiration as we have this short growing season here, and obviously the water sits in these pools on the surface. In the winter, there is very limited evapotranspiration because there's very little vegetation at that point. Here's an example of those pools of water, and we said so when the temperatures rise, the snow on the surface and active layer starts to melt. It turns into these ponds and lakes, which you get kind of thousands of them. And as I said before, it doesn't infiltrate because that permafrost layer below the active layer remains frozen for the entire year. Another factor that plays into how the water cycle acts is geology. So much of the tundra is made of this Precambrian igneous rock, which would mean that it's very, very impermeable. And therefore, because of that, that aids that standing of the water. Not only have we got that permafrost layer, but we've got a geology below that which prevents any water going down, percolating down into kind of any potential aquifers. So when the temperatures do go up, we get these standing pools of water in the summer period. And just to show how extensive some of this geology is in terms of its uniformity, the Canadian Shield is an example, which is a huge area of Precambrian igneous rock. And it's that big red area you can see. So it takes up millions of kilometres, and we see similar rock types also in Siberia and other parts of the Arctic tundra. So we get a pretty uniform amount of geology. There are kind of metamorphic rocks as well, but again, they would have low permeability also. Last thing to consider with all these physical factors is that much of the tundra is very, very flat. We get very uniform relief. There are some areas with gentle slopes. There would be also some areas in the lower Arctic where it would be kind of more like forest and have some slopes. But because most of it is this low relief and we have this permafrost layer, again, this aids the fact that there's little infiltration. In the winter, most of the snow is going to stay on the surface, and the flat relief that you get in the summer means the water stays on the surface in these pools rather than draining away or infiltrating into the surface, or even if it had very steep slopes, it would run off and form lots of rivers. You will get rivers being formed as this water will eventually make its way into rivers and streams, but essentially lots of it going to sit on the surface and waterlog, and so we would see that happening largely down to the relief and the permafrost and the other factors that we've already discussed.